Next, we're going to be taking a look at linear and exponential growth. So we want to understand first off, what is linear and exponential growth so that we can begin to look at how they vary, what are their differences. So let's start off with a pair of definitions. Linear growth occurs when a quantity grows by the same absolute amount each unit of time, versus exponential growth occurs when a quantity grows by the same relative amount each unit of time. Now I should note, I'm saying growth, but if things can grow, they can also shrink or decay. So we can also look at linear decay and exponential decay, meaning lessening, things that are going down. And so the key here really is the absolute versus the relative. Those are the key things that we wouldn't be looking for. So what we'd see in the case of linear growth, let's say we have times and amounts. I'm going to just leave this as a unitless thing right now, but if we have time to 0, meaning our starting point, if we have 10 units, if we go 1 unit of time, so maybe 1 second, 1 minute, and maybe the amount's up to 12. Well, what that means is we've just seen an increase in 2. Every unit of time from here, we have to continue to see that increase of 2. So at time 2, we get an amount of 14 because we've gone up by 2. At time 3, we've gone up to 16, and we could do this all day long, but what we see is that the amount is going up by 2 every single step, every single time interval. Versus, if we look at exponential growth, we see that it's increasing by the same relative amount. So let's look at time versus amount in this scenario. If I start at time 0, we'll assign the same initial value of 10. This time at time 1, I'm going to say it's gone up to 20. If we look, that's an increase of 10 units. So if it's linear growth, we would expect 30, and then 40, and then 50. But what we see with exponential is at time 2, we've actually jumped all the way to 40. We've skipped over that 30. And then by time 3, we're up to 80. Time 4, we're up to 160. Now I've just arbitrarily chosen the growth pattern itself, but what we can see is the absolute amount was going up by 10, but then it went up by 20, then it went up by 40, then it went up by 80. That number is changing, and it's actually doubling every single time. What the pattern actually is times 2, times 2, times 2, times 2. So the amounts are going up still, but the pattern in which they're going up, that number by which they're going up, is changing. We can also view this through their graphs. Linear graphs we're going to study more, but what we see with linear growth is a straight line path. The amount it is changing by stays constant. The graph itself is not staying constant. Our y values are obviously changing, but if I go up 1 and over 1, the next unit of time I go up 1 and over 1 as well. Compare that with exponential. We see things are happening faster and faster as it goes along. Start off maybe by adding just 1 or 2 units, or getting into maybe 2 or 3 units, 4 or 5, but now one step, one single increment of time is representing a much greater amount of change than it did in that previous increment of time. So that's what we want to be on the lookout here for linear and exponential growth. So let's give a couple examples of how these could appear. So an example of linear growth. The temperature inside a car increases by 2 degrees per hour until noon. So here we have an example of linear growth. We see that same amount of growth every single step, 2 degrees every single time. All right, let's look at an example of exponential growth. The population of deer in the woods increases by a factor of 2 every week. I've given 2 different, let me shrink this down so we can see them both at once. I've given 2 different increments of time. That doesn't matter, right? We have per hour versus every week per week. The key is every 1 unit of time increase, how does the dependent variable change? So we can see the temperature increased by 2 degrees, set amount 2 every single time, versus the deer population increasing by a factor of 2, meaning it doubles, factor of 2 times 2. So same idea as before. If we start with 10, then we get 20, then we get 40, then we get 60. And so anytime we see a doubling or a tripling or a halving, those are all indications of exponential growth. It can be growth or decay. So we could see something where Sally loses 5 ounces of weight every week she is on her diet. Now we actually have a decrease, our unit of time every week, but that amount of loss, 5, every single week. And so it is an absolute amount. Diego sees a 10% reduction in the number of errors in his code every assignment. So Diego may be in a programming class submitting his code each assignment. Every single time he sees a 10% reduction. That 10% is not a set number. So for instance, if Diego started maybe with 20 programming errors, the 10% of 20 would be 2. The first week he sees a 2 error reduction, and then we take 10% of that new number, 18, it'd be 1.8. So anytime we see these percentages always indicate a growth or a decay that is exponential in nature. So again, what we want to be looking for is every unit of time, how is that change occurring? Is it by a set number, X units? However, whatever our unit is, ounces, degrees, pounds, inches, is that occurring by a set unit, or do we see a percentage or a factor increase or decrease?